Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over how to perform dilutions, and if you have any questions, make sure you ask tomorrow. Fill in everything as you see in your note packet. Okay, so dilutions. Often chemists batch up extremely concentrated solutions, and we call these stock solutions. Now, it's not just because we put them in our stock room where we stock all of our chemicals. They call them stock solutions because they are heavily concentrated. So what do we mean when we use the term concentrated? Recall that concentrated means that there's a lot of solute inside of a solution if it's very concentrated. So the reason why, what would be the point in buying extremely strong chemicals? Like if I had to buy chemicals, why wouldn't I just buy it already, sort of diluted down to the concentration that I want? Well, the reason why is because if you buy a stock solution, you can always dilute it down. So I could technically take an extremely concentrated solution of, let's say, 16 molar HCl, and by adding water, I can literally turn that into anything lower than 16 moles. So I could make 12 molar HCl, or 10 molar, or 5 molar, or 1 molar, or 0.1 molar, or 0.01 molar. But I can get all of that because all I've got to do is take my concentrated solution and add some water to it, and when I do that, I get, sort of more dilute solutions. So dilutions are kind of like a key part of chemistry because in order to get reactions to work, sometimes you don't need the concentrated stuff. You can actually use something pretty dilute. And obviously we don't want to be wasteful. Concentrated stock solutions are very expensive. How exactly do we perform dilutions? Well, the performance makes it sound like you're going to play an instrument or something, but performing dilutions is kind of like a standard lab skill that you're going to be using quite a bit, especially in this unit, but also in the next couple. So performing dilutions using a stock solution is kind of like an essential lab skill that every chemistry student kind of needs to know. And what we use in order to figure out what concentration our new solution will be at after we've added a sufficient amount of water to dilute it is the dilution formula. And actually this one right here is the dilution formula. It's not this one. This one explains, though, why the dilution formula even works, okay? But M1 times V1 equals M2 times V2, all right? It looks like one of our gas laws, actually, but it's not. It's molarity and volume. So M1 is our initial or starting molarity, V1 is our initial volume, M2 is our new molarity, and V2 is our final volume. And by simply, sort of multiplying those and setting them equal to each other, you can figure out the missing piece of anything. So if I know M1 and V1, and I know M2, I can find V2. If I know M1 and V1 and V2, I can find M2. If I know, and I can repeat that again, you kind of get what's going on, I can kind of use this equation to find any missing piece of the dilution formula. Now, why does this work? This works because of, like I said, this guy right here, M times V equals moles. Now, that's apparent if you think of the units. So remember, molarity is measured in moles per liter, and so obviously if I multiply that by a unit of volume like liters, everything cancels out and I get moles. But the real logic behind this, it makes a little bit more sense when you draw it. So you don't have to draw this, but I'm going to. All right, let's say this is my beaker, and this is how much I have. And then my solute is floating around. So if I wanted to, I could count how many moles of these little black particles I have. Well, what happens when I dilute something? Well, when I dilute it, I add water. So now it's up to here. What happened to my particles? Did I gain more particles? No. The amount of moles of particles stayed exactly the same. All I did was I changed the volume. So now the water level is not down here. Now the water level is just up a little bit higher. But I didn't actually lose or gain any of, the tiny little microscopic particles. So diluting something down does not change the number of moles. And that's why this equation works, because the number of moles on this side of the equation is equal to the number of moles on that side of the equation. They don't change. They're constant. Let's do some examples. Example, what volume of 16 molar stock solution must be used to prepare 1.5 liters of a 0.10 molar solution? Okay, so anytime I have two different molarities, or I have, sort of changing volumes because I'm adding or subtracting liquid, that's going to be the dilution formula, because that's what dilutions are. So I'm just going to write that down. M1 times V1 equals M2 times V2. Now here's my method of solving dilution questions, and it might help you, it might not. But I always like to draw a little picture so that I kind of understand what's happening. And so I'm going to draw my little picture over here. So that sort of large blob and smaller blob are going to be beakers of stuff. Okay, and in here I'm going to have my 16 molar solution, and over here this is what I want my final solution to be. So I want my final solution to be a 0.1 molar solution, and I want it to have 1.5 liters worth of volume in it. Okay, and so the question here is, what volume of this 16 molar solution do I need? How much do I need to start with? Question mark. Like, this is my X. I don't know what it is. So that gives me my 16 molar solution. I have that in my picture. I have my final volume, and I have my final molarity all over here in this picture. So really, the question is, how much of this would I need to add in order to kind of get up to the correct amount? So let's solve that. So M1 times V1 equals M2 times V2. So I have 16 times X equals 0.10 times 1.5. So what does X end up being? It ends up being a tiny amount, 0.009375 liters. Now here's the thing about that number. Because we're talking about, 16 molar stock solution, obviously I'm not going to have to add very much of my concentrated solution in order to get, sort of a correct, low concentration amount. That just kind of makes logical sense. If you're going to need to dilute something down, you don't need to use very much of it if you start off with really strong stuff. But it might be a little bit more apparent if I actually convert that into milliliters, just so you can see how many milliliters that is. So remember, when you multiply all of this stuff out, you multiply by 1,000, in order to get milliliters. So that equals 9.4 milliliters. Okay, and so of course, if you use a tiny little amount of something, it's going to, get diluted down pretty easily with water. The other thing, though, is if I'm using significant figures, I should say this is 0.0094 liters. I don't want to give, the illusion that I have more precision than I actually do. This next question is probably the strangest question out here, but because making solutions is so important, we have to kind of describe how could you prepare a solution like the one that we just calculated. So here's the first step, all right, and this is just like a good, sort of answer to almost any lab-based question, all right? You are going to need to make sure that everything has been cleaned and dried, all right? Everything has to be cleaned and dried. And so I'm going to be talking about it. What I write down is not exactly what you need to write down. You can be as detailed as you need to be, because this is really going to come in handy when we do our formal lab. So everything has to be cleaned and dried. Why? You don't want any residue of stuff stuck around, because that could throw off a lot of your calculations. The next thing is you would need to get, 9.4 milliliters, okay, of your solution, that you started with. So of your HCl, and that was our 16 molar HCl, so our very concentrated stuff. How are you going to get 9.4 milliliters? Well, we want to use something called a volumetric pipette, and we'll be using quite a bit of these volumetric pipettes. So we want to use a volumetric pipette because that gives us a nice accurate measurement. And so yeah, you can probably find a volumetric pipette that measures exactly 9.4 milliliters somewhere in the world. Next up, after that, you want to make sure that you have a nice, clean volumetric flask, okay? And so that volumetric flask is going to have an amount of exactly 1.5 liters. I guess that doesn't really look like a point, so 1.5 liters. All right? What you take is we're going to take, for step 4, okay, I don't want to rewrite this, we're going to take our 9.4 milliliters of HCl, we're going to put it inside of our cleaned volumetric flask, 1.5 liters, and then for step 5, we add distilled water. Okay, it has to be distilled or deionized. Okay, so add distilled water until you get to 1.5 liters. After you've done that, shake it up a little bit and you have your solution prepared. Okay, that's really it. So make sure you follow along with those steps. And again, like I said, I described it. So make sure you write those down. Clean and dried. Everything has to be cleaned and dried. 9.4 milliliters of this in a volumetric pipette, 1.5 liter volumetric flask, nice and clean. Add both of those together and add distilled water until you reach your final volume. This is a great question. Example, what will the molarity be if you dilute 50 milliliters of a 0.50 molar solution with 150 milliliters of water? Notice I underlined the word with. And the reason why is that this is a very common mistake because people know the dilution formula, M1 times V1 equals M2 times V2. So rather than reading actually what the question is, they just blindly start plugging in numbers. Okay, so let's actually look through this. What will the molarity be? So I already know I'm going to be looking for molarity. If I dilute 50 milliliters of a 0.5 molar solution with 150 milliliters of water. Now based on all of those things, I like to still draw my picture. So I'm going to still draw my picture. I have my little and I have my big container. Let's try to fill in my weird little picture. So it says that I'm diluting a solution that is 0.5 molar in concentration, and I'm starting with 50 milliliters of this stuff, so that's 50 mLs inside of my little container. I'm diluting it with 150 milliliters of water. That is important. So now I'm going to, sort of add it to my large container, and I'm diluting it with more water. Okay, now think about this. If I already have 50 milliliters, and I'm diluting it with 150 milliliters, how many milliliters is this solution going to now contain? 200. 200 milliliters. If you had just blindly read this and not noticed that it said that I'm diluting something with 150 milliliters of water, you would have put down just 150. You wouldn't have even thought about it. But again, when I say I'm diluting something with water, that's the important thing. I'm adding water if I'm diluting something with water. So, what is my molarity? Question mark. I don't know what that is. I have no idea what my what my molarity of my final solution is going to be, and it's up to me to find out. So let's do that. All right, I have my 0.5 for my molarity, my initial starting molarity. I have 50 milliliters. Okay, I have my final molarity as being X. I don't know what that is. And I have 200 milliliters. This brings up a really important point. Notice that as long as my units are the same, when I do my division and everything, they end up canceling out. So technically, I don't need to worry about converting everything to liters, even though, okay, molarity has to be measured in moles over liters, because it ends up canceling out in the equation. If that's going to really bother you, you can, but you'll get the same answer. It's because of the relationship in the equation. Because moles equals moles, okay, because M times V equals moles, it doesn't really matter what your unit is as long as it's just the same unit on both sides. So let's solve this. So what do I need to do? I need to divide this by 200 milliliters, divide this by 200 milliliters, and again, notice everything cancels out actually. And so I'm left with a molarity of 0.125, and that's capital M there, okay? And that would be my molarity. If I'm using actual significant figures, though, it would be a molarity of just 0.1, okay? Because I only have one significant figure in 50. But there you go. That's how you'd find the molarity of this dilution. Next example. Example, you need to make a 5.0 liter solution of 1.0 molar sodium nitrate. What molarity would the sodium nitrate solution need to be if you start with a 2 liter solution? Alright, so again, I'm going to underline important pieces of information. I read the entire thing though. So 5 liters, 1.0 molar NaNO3. I'm asking for what the molarity would be if I start with 2 liters. So again, let's just sort of draw my weird picture. And so in my starting solution, I actually don't know what my molarity is. So I know I have 2 liters of something, but I have no idea what my molarity could be. I know, though, that I want my final solution to be 5 liters in amount, and I want it to be a 1 molar solution. So what does my starting molarity need to be in order for this to work? Let's write my equation. So this is our molarity equation. All right, next up, let's plug in what we know and what we don't know. Don't know what my starting molarity is. I do know I have 2 liters to start, though. I do know that I have a 1 molar solution and that there are 5 liters of it that I want. So what do we end up doing? Well, when we work that out, we get 2.5 molar solution. And that just makes sense, because if I have a 2.5 molar solution, and that's 2 liters, and then I dilute it with 3 liters of water, of course, my concentration is going to go down, and it just so happens to go down to 1 molar solution of something. So that's it for the dilution formula. Make sure that if you have any questions, you ask tomorrow. But something that I didn't get a chance to actually do an example of or talk about is that, remember, that since I can find the number of moles using the molarity formula, I can technically convert that into grams. So if I wanted to really extend this, I could actually involve gram and mole calculations as well. Other than that, if you have questions, talk to me tomorrow.